remained an unknown entity until BTDK made Pauli postulate my identity. I interact weekly only during very close encounters, so emerge smiling after the Earth I traverse. With a sociable me, sun would conk off much earlier. In all probability, there too I wouldn't find you here. Up the sleeve, I have several uncanny tricks, acquiring mass thanks to a rotation matrix. Schizophrenic traits I happen to display, flipping personalities like child's play, full and precise characteristics of all my three flavors, reasons for low abundance of our conjugate partners, magnetic particles. Ascertain these in a deep down tunnel experiment on particle physics theories you may hence make. So this is written by Apurva. Thanks, Apurva. Okay, so now I come to a quick recap of neutrino oscillation. This is relevant to mass measurements, as I will show. So we already know that neutrinos mix, and for the simplest case of two-flavor mixing, uh, the leptonic eigenstates nu e and nu mu can be written in terms of mass eigenstates nu1 and nu2, which have masses m1 and m2. And then there is one mixing angle here for the two-flavor mixing, that's theta. And if you calculate the probability of a nu mu remaining a nu mu, what is the so-called survival probability, then that can be written down as 1 minus sine squared 2 theta, where theta is the same mixing angle, times the sine squared, some factor, small of the order 1, into delta m21 squared L by E, where delta m21 squared is nothing but the difference in mass squares of the m2 and m1 is the propagation. This is, of course, this is true for vacuum oscillations. These quantities like theta, delta m1, and so on, they get modified when neutrinos propagate to magnitude. Okay, so if delta m squared is in EV squared, E is in MEV, then L is in meters. Okay, so whereas if E is in GV, then L has to be written in terms of kilometers. The point to note here is that if theta equal to not if theta is equal to 0, then there is no mixing. Similarly, if delta m21 squared is 0, then again there is no mixing. So if you observe oscillations, both of these quantities have to be non-zero. That's point number one. The other thing is that these oscillation measurements give you only the difference in mass squareds. They don't give you the absolute mass. Okay, so this is another important point. So you cannot set the scale of the mass from these measurements, but you can tell the difference in mass squareds from such measurements. Okay. Of course, in reality, we have three flavors. We have the E electron type, muon type, and the tau type. So you have actually a 3x3 unitary matrix, as Uma Shankar pointed out, Uma Shankar and other people also. This was discussed somewhat extensively then. So just for the purposes of this talk, I just need to say that delta m21 squared is about 30 to 40 times smaller than delta m32 squared. Also, we know the sign of delta m21 squared. In other words, that m2 is greater than m1 from solar neutrino experiments. Whereas we do not know the sign of delta m32 squared. In other words, we don't know if m3 is larger than m1, m2, or the other way around, it's smaller. Because of this difference, as you can see on the right top side figure, that you have a m1, m2 close by, and then you have m3 in the so-called normal hierarchy, where you have 1, 2, 3 in terms of increasing mass. Or you could have the inverted hierarchy on the right side, where you have m3 below m1 and m2. Okay? This will be important when we discuss neutrino-less double beta decay. The other thing is that the mixing angles are rather large. So theta 1, 2 is of order 30 odd degrees, theta 2, 3 is of order 43 degrees or so. This is a slightly older tabulation. Theta 1, 3 is about 8 degrees or so. But a recent experiment, as Urjit showed, the T2K collaboration, which was published very recently, towards the end of April, is that the delta Cp, which is a measure of the asymmetry between neutrinos and antineutrinos, is rather large. It's in fact close to maximal. Of course, the significance of this result is at about 3 sigma level. So, I mean, in particle physics, the standard is 5 sigma. So, hopefully, hyper K, which has been approved, which is an experiment which is about 10 times bigger than the super Kamiokande, that will build on this and either support this measurement or maybe dilute it. But this is an extremely important result if shown to be right. Okay, so now we come to some basic properties of neutrino. There are many. I will discuss only mainly mass measurements, but also a little bit about violation of parity, because this is something that is pedagogic, and I think it would be good to tell about it, especially for the benefit of students here who are not so familiar with this. And also a beautiful measurement of the helicity of the neutrino. It happens to be a really unique case, and this was using radioactive sources that was done way back in 1958. But it's a classic because there's no other case where this helicity can be measured in such a beautiful manner. Okay. So, as I said, the mass measurements fall into so-called direct categories and slightly indirect methods of measuring the mass, including the neutrinoless double beta decay, in which no neutrino is emitted, only two betas are emitted. This was actually discussed in some detail by Vandana Nanal about, I think, a couple of weeks back, 2 or 3 weeks back. Then there are astrophysical bounds on mass of the neutrino. And finally, there are also cosmological bounds. So I will discuss some of this in less or more detail. Okay. So first of all, we should ask the question, why should you measure the mass of the neutrino at all? What's its importance? Now, the so-called standard model, which explains all that we know of in electron physics and quark physics and so on. So weak processes, strong processes, electromagnetic processes. So the standard model has the mass of the neutrino as identically zero. So they're left-handed particles, and a neutrino has zero mass in this model. So the fact that the mass of the neutrino is finite and not zero already means that we have to go beyond the standard model. So neutrinos have provided one of the early clues that the standard model is not all. We have to go beyond it. In particular, if the neutrino is the Majorana neutrino, then the seesaw mechanism could come into play. And if that mechanism is right, then there are light neutrinos and then there are heavy neutrinos. So we have, by measurements at of the low mass neutrinos, we have probably access to the ultra high energy scale corresponding to the heavy neutrinos, which are of the order of whatever 10 to the 10 or so GeV or so, or maybe beyond. And these energies are not in the reach of at least accelerators that we can foresee. So this is one very important reason why we should study these tiny neutrino masses. There is this question of, are there heavier neutrinos, including so-called sterile neutrinos? So people have been searching for heavy neutrino mixing in the EV, in the KEV scale, and I will say something about it in one slide. So if there, for instance, if there were too many heavy neutrinos, they could have accounted for the dark matter in the universe. But it turns out that some of the measurements that pointed in that direction, which gave neutrinos a mass of between, I think, something like 14 and 46, it turned out to be not correct. There were atomic effects that caused these experimental measurements to be what they were. And therefore, now the neutrinos are known to be less than a couple of electron volts. So anyway, so that part is out, and we are looking for light neutrinos. But there could be a small mixing of heavy neutrinos. Okay, and so this is one of the reasons for looking for the mass of the neutrino, at least heavy mixings. The other reason is that heavy neutrinos have, or non-zero mass neutrinos have implications in cosmology. As I said, if they have a large mass, even if they cool down, they will, of course, have gravitational interaction, and they will they will affect the large-scale structure of the universe. If they are relativistic or non-relativistic, they'll behave in somewhat different ways. And therefore, it is important to know what the mass of the neutrino is in terms of its effect on cosmology. Okay, so how do you weigh the neutrino? As I said, there are direct measurements. By, of course, direct, I mean you cannot take a neutrino and weigh it. Rather, you measure the energy momenta of the particles that are associated with processes that involve neutrinos. So for instance, beta decay is the process which actually led Pauli to propose the neutrino. And Fermi was the first one to propose that you could measure the energy spectrum of beta particles near the endpoint, and you could infer already in his days, you could infer that the mass of the neutrino is less than kilo electron volt or so. Of course, you can get more precise if you measure very carefully the spectrum near the endpoint to within electron volts or even within hundreds of milli electron volts. Now, since you have to measure things near the endpoint, low endpoint energies are preferred because then the fraction of those events near the endpoint is larger as compared to the total number of decays. And so the classic case that has been looked at since the last 60 or so years is the case of the beta decay of tritium, which is a heavy hydrogen, 3 times heavier than normal hydrogen. It has an endpoint energy, that means the maximum energy of these beta particles is about 18.5 keV. And so you look for the small changes, which I will show in the next couple of slides, in the electron volt region away from the endpoint. And there is another case of 187 rhenium. It is somewhat more difficult to measure this, and at least it is because it's not there in such, you cannot make it in such large quantities. The decay rate is rather small, so you have to have an array of such detectors and so on. But in any case, that has been also looked at and has provided limits somewhat worse than the limits which have been obtained from tritium. Then there is this case of radiative electron capture. You must have heard of electron capture. This is something that when an electron in the K or L or M orbital, depending on the Q value of the reaction, gets captured by the nucleus and leads to a nucleus which is 1Z away, Z minus 1 as compared to the original Z. Now, in that process, of course, a monoenergetic neutrino is emitted, but you can also have a radiative transition. So you can have a radiative electron capture. You can have a photon emitted by the electron. So this is a higher order process. Of course, it's weaker by about a factor of 10 to the power of 5 or a million times weaker. But then the measurement is simpler because instead of measuring a charged particle, you're now measuring a photon. And photon measurements are, of course, easier. You can also get very high energy resolution with the detectors that we have nowadays. And so this is a possible competitor. And so this was first proposed by the Hula, where he pointed out that you can have a resonant enhancement near the endpoint, and that can lead to a better measurement. Of course, you can also measure the energy momentum of particles in the final state in the decay that involves a neutrino. And this is done, for instance, in the case of a pion, where a pi decays to muon and nu mu in the case of or it can decay to an electron and a nu e. And for instance, if you measure the energy momentum of the muon, it's a two-body decay, so you can infer what is the energy momentum of the nu mu, and then from using relativity E squared minus P squared, you can get the invariant mass of the neutrino. Of course, these limits, these measurements give bounds, upper bounds, but they are much poorer than in the case of the electron type of neutrino. So they are typically of the order of tens of keV, or in the case of the nu tau, where you look at the 3 or 5 body decay of the tau particle, you get limits in the region of MeVs, tens of MeVs. I've just written this down for completeness sake. Okay, there is another method of measuring the absolute neutrino mass through the Neutrinoless double beta decay. So that's zero neutrino, 2 beta decay. It's a higher order process. We all know beta decay, but this is a decay process which is much weaker, in which 2 betas and 2 neutrinos are emitted. That is in the case of 2 neutrino, 2 beta decay. But if the neutrino is a Majorana particle, in other words, it's its own antiparticle, then as shown here, a nucleus A with the Z number of protons can decay to A with Z plus 2 protons, so 2 less neutrons, and it can emit 2 beta particles and no neutrinos. So everything is charged in the electrically charged in the final state. You can measure these 2 betas and then look for such a process if it exists. As I said already, this process is possible only if mu e is equal to mu e bar. That is, it's its own antiparticle, and therefore that's called a Majorana particle. That's jargon for that, because Majorana was the first to point this out. Now, the rate for this process is proportional to the phase space, proportional to the neutral matrix element, overlap of the two wave functions of the initial and final state with a Hamiltonian in between, and also to the effective mass of the neutrino squared. What is this effective mass? This is given by a summation over the mass eigenstates times the UEI squared. This is the mixing matrix element. Now we know the values for these mixing matrix elements. So UE1, for instance, is of the order of 0.8 or so. UE2 is of the order of 0.6, and UE3 is of the order of 0.1. Now let us just see what happens in the two cases of inverted. Uh, there is a just hold on. There's one phone call coming. I'll just say that. Hello, Govinda. I'm giving a talk. I'll talk to you later. Okay, so the in the case of inverted hierarchy, you can see that M3 is lowest, and M3 times UE3, this is small, but then M1 and M2 come with much bigger contributions. So for the inverted hierarchy, if the minimum neutrino mass is something, then you have the highest effective M nu. On the other hand, for the normal case, where you have M1 lowest, M2, and then M3, that M3, which is largest, comes with a small coefficient, only 0.12. Okay? So for the small minimum neutrino masses, this is much smaller than the inverted, by about a factor of between 50 and 100. Okay? So the present experiments are actually sensitive when they are the best that they can do to the inverted mass hierarchy. And presently, the two big experiments called Zen Kamland and Cure have put these effective masses as 0.11 EV by C squared and 0.24 by EV squared. So we are probably not having inverted mass hierarchy. Of course, there are errors on this. And the main error that comes here is from the nuclear matrix element, which can be off by a factor of 2 to 3. Okay? So that's so these limits are with this caveat that there is an uncertainty in the nuclear matrix element. But nevertheless, they give a measure of a certain mix of the neutrino masses, of the absolute neutrino masses. Okay. Another way of measuring the neutrino masses is by using a time of flight, the time of arrival from a very strong source. And of course, you need large distances in order to get small time differences, because after all, the neutrino is relativistic. Okay, the neutrino, let's say an MEV neutrino is highly relativistic. So a small, mass, whether it's 1 EV or 2 EV, that would make a very tiny difference in the arrival time if you are talking about terrestrial distances. However, if you go to galactic distances or even maybe extragalactic distances, then it's possible to get bounds or to even measure if you have a finite neutrino mass, that quantity, using the time difference between different energy neutrinos. Now, uh, one of the cataclysmic events in which neutrinos are produced in large numbers is so-called supernova explosion, in which the star collapses on itself. And in the initial part of the collapse, the electrons and protons combine to give neutrons. So that's the so-called neutronization burst. It takes place over a period of something like a few seconds. And if you calculate the time difference between a neutrino reaching from, let's say, 10 kiloparsec and a photon, and so of course different energy neutrinos would have different times, so then you would take a difference of the difference. So then this is given by some constant times the distance, of course, into m nu by e nu squared, whole squared. So the larger the mass of the neutrino, the larger would be this time difference. And of course, the quantities in which units these are measured, milliseconds, kiloparsecs, EV squared, and in terms of 10 MeV, they are given here. So if this measurement, we have only one measurement of a supernova explosion, neutrinos from there. That is SN 1987A. This was talked about by Amol in his talk, but also by, I think, Shurvati and maybe one more talk. So we know what should be the time dispersion of these neutrinos from models of supernova explosions. However, if there is some deviation from that, then you can attribute it to a possible non-zero mass of the neutrino. And people have done very careful analysis of this. Of course, there is some model dependence on that, but the upper limits on the m nu that you get, this is one of the references given here, is something like a few electron volt, 6, in this case, 6 electron volt by c square. Okay, so this is a reasonable bound. This may improve if we get to measure a supernova with the bigger detectors that we have. These measurements were made with the detectors that are about 10 to 30 times smaller in size. And also we have now better ways of detecting these. So we should get typically 100 times or so the events that we had. We had only about a handful of events, 10 to 15 events. If a supernova explosion occurs, which is due to occur anytime now, because typically the time scale is 30 years. So 1987A is already 33 years more. So we should expect a supernova anytime in the next 5-10 years. If that happens, then we would be in a much better position to measure this. And so this quantity would decrease, the upper bounds would decrease considerably. There are also cosmological constraints on neutrino mass. So Kaushik and McClelland were one of the early investigators of this. Kaushik was a member of TIFR at that time. They considered the effect of finite mass, so it would change the expansion of the universe. And from what we know from observation and from the model of the universe, cosmological model at that time, they could infer that the sum of the masses was of the order of 17 eV. At that time, only 2 species of neutrinos were known. Remember that this is 72. The third neutrino was only discovered in 2000, much later. And so, if you translate this into recent analysis, then this translates to about 8 eV squared by c squared. And present analysis, which is much more sophisticated, which looks also at cosmic microwave background radiation, the effect of massive neutrinos on this cosmic microwave background, then this can be sharpened considerably, in fact, by a couple of orders of magnitude, and this reduces to about 0.14 eV by c squared. Of course, there is some model dependence, but I mean, cosmologists say that this is a reasonable estimate of the upper bound on the sum of the mass of the neutrinos. So you can see that this is, we will see that the bounds that are higher than this, of course, they hope to get to this in a few years' time. We'll come to that later. Okay, so the workhorse for lab measurements of the neutrino mass has been the measurement, as I said, of the beta energy spectrum of low Q value or low endpoint energy beta decays. And so this is a picture taken from a textbook, Introductory Nuclear Physics by Wong. So you can see that if you make a so-called Fermi-Curie plot, in which you plot the rate of a certain momentum of electron divided by the momentum squared times a so-called Fermi function, and plot it as a function of electron energy, then this is a negative slope and it falls with energy of the electron, and it would be a straight line if the mass of the neutrino is 0. If it is non-zero, then the shape changes. In fact, it has, for this quantity, there is an infinite slope at an energy which is given by the endpoint energy minus the m nu c squared. Of course, these things are washed out a bit if you have finite resolution of the detector. Uh, and then what is shown with the finite is this, the, the dashed line if it is zero mass, and if you have finite mass, it is this black line. The beta decay endpoint energy, by the way, has been measured with great precision. In fact, more precise than what is required. So that is not going to be the cause of error in the neutrino mass measurement. Okay, so the electron spectrum in beta decay, the energy differential rate dN by dE is given by some constant, which depends on Fermi coupling constant, or which I said, which is basically saying what is the distortion of the Coulomb electron wave function in the final state, times the PE. These are phase space factors. P times E times Q minus E. Q is the endpoint energy, the maximum energy of the electron for m nu equal to 0. And now, since we know that neutrinos mix, it is a summation over this UEI squared, which is the elements of the mixing mass matrix, uh, but with respect to the electron. So it's only the first row in that 3 by 3 unitary matrix that come in, times a Q minus E whole squared minus m nu I squared to the power of half. So the whole thing is summed over the three mass states. Okay, so the spectrum is like this. Look at the spectrum plotted here, the count rate versus energy. And towards the end point, if you blow it up, then this is what you see. This is taken from a paper from the Katrin collaboration, the one which I will talk about presently. So if you have zero mass, then put in the finite resolution of the detector. It's a magnetic electromagnetic spectrometer actually. Then you get the red line. If you have a finite mass, you don't get you get it with an endpoint which is somewhat smaller, 1 eV smaller, and the total number of counts that are effective, which you have to actually look at, is only 2 into 10 to the minus 13 of the total events that you have. So you can see that this is a very tiny part of the spectrum. So it takes a very strong source to do it. It also takes time to measure the spectrum very precisely at the end point. Okay, so I hope I've conveyed that measuring the energy spectrum very precisely at the end point or close to the end point is what will tell us about the finite mass of the neutrino. Okay. So the early experiments started with tabletop experiments. In fact, we also had some small measurement. I will come to that in the 17 kV neutrino case. But they were all small size experiments, magnetic spectrometers or silicon detectors and so on, all that could fit in a small room and so on. The most, I mean, the present experiment which is being done right now for, and an early measurement of that, which I will show you in the next slide, is from the so-called Katrin electron spectrometer. So this is a electromagnetic spectrometer. It uses molecular tritium source, which is, many curies. It's of the order of 3 curies. So there are 10 to the power of 11 decays per second. So handling this can only be done in labs that are capable of doing this. It is done in the Karlsruhe lab in Germany. It uses molecular tritium. It basically filters out electrons which have energies which are less than about 50 electron, 40, 50 electron volts. And with this so-called quote-unquote junk electrons removed, then it looks very carefully at the electrons near the end point. And so you can scan the retarding field from minus 40 to plus 50 around the end point. And so it's a kind of integral measurement. If you stop electrons that have 50 eV away from the end point, you get all of them coming. You can increase the voltage so that you stop only those which are below 40 and 30 and 10 and so on. And you can scan this field and then you get a measurement. And that you can compare with what you expect. Look at the size of this experiment. So from tabletop now, this experiment has gone to a length of the detector, which is about 70 meters. Okay, so there's a windowless gaseous molecular tritium target. This, of course, is in closed loop, so you don't want this radioactivity to escape, or at least if it escapes, it's very tiny, which is acceptable in terms of its health physics requirements. So then it goes through a focusing system. So you have a magnet which focuses and transports these electrons into this spectrometer, where you have a retarding field, and then you have a so-called adiabatic magnetic field. So the electrons recess around this around the magnetic field, and then reach go from here to here, where you have an array of silicon pin diodes, I think cooled also, to detect the electrons. In fact, after you retard them later, just before the detector, you even accelerate them so that the response to these electrons is uniform, irrespective of what is the decelerating voltage that you have. Of course, which is scanned anyway over only about 100 volts. So this is a very simplistic view of this. It's very complicated. I mean, there are many tiny effects that would vitiate such a measurement. But at the end of it all, they have taken care of all these systematic effects. They have vacuumed to the order of 10 to the minus 11 millibar and so on. So you have minimal effects of the residual gas particles that hang around. You have to take care of surfaces because they can emit secondary electrons, and there are many things. So this measurement, although was proposed in about the early 2000s, has taken so many years to build, and it's only now that the first measurements have come in. And the first measurement, which has come in PRL in 2019, about 6-7 months ago, show that we have an upper bound on the mass of the effective mass of the electron neutrino. As I said, it's a sum of the UEI squared times MIs. And that comes out to be about 1 electron volt by C squared. This improves on the previous bound by only about a factor of 2. But on the other hand, this is just from the first 1 month run that they had. And in about 3 years' time, if all goes well, they will be able to improve this bound to of the order of 0.2 eV by C squared. Indeed, if they find a finite mass, let's say 0.5 or so electron volt, then that will be a great discovery. This will be a great result for all. And but if nature is unkind, they will produce a bound to the level of about 0.2. So about a factor of 10 better than the last bound, which was measured in about 2002 or so, 2002, 2004. Okay. So as I said, this is the dots with the errors. They are the data points, and the blue line is what is expected. They have a background measurement beyond the endpoint, which is very precise. And the residuals are shown here in terms of sigma. So you can see that they are mostly within 1 sigma. What is shown is statistical as well as systematic errors. Forget about this. This is just showing the time, amount of time that was spent on a particular retarding voltage. And anyway, the final result is this, and this gives this limit. Okay, what if this ultimately this measurement also shows only a bound, and we only at the end of the Katrin set of measurements are only able to say that the mass is less than 0.2 eV squared. There is a completely different way of measuring the mass through the radiation that an electron emits when it moves in a magnetic field. As you know, suppose you have an electron of a certain momentum, it precesses in a constant magnetic field, right? In fact, it performs a helical trajectory if it is not perpendicular to the magnetic field. And so there is a parallel motion and there is a perpendicular motion. The so-called cyclotron frequency, when it moves in a magnetic field, is omega c, which is given by the charge of the electron times the magnetic field divided by the total energy of the electron, which is just the rest mass plus the kinetic energy of the electron. Now, of course, since it is accelerating, it also radiates, and it radiates at the cyclotron frequency. So if you can somehow measure this radiation, then you can tell what the kinetic energy is. It might look like a very small effect, but it's not very small. It's of the order of 50 ppm at 18.6 kV if you have a magnetic field of about 1 Tesla for a 1 eV by c squared mass. Of course, the cyclotron frequency, F, which is just omega c by 2 pi, is of the order of 30 gigahertz or so, which is perfectly in the realm of measurements. The power that is involved in this is very small. It's only of the order of femtowatts. So when this 18 point, you have to make measurements, of course, in the region of 18.6 kV, which is near the end point. it radiates, but the amount of energy that it radiates away is very tiny as compared to the energy itself. So this is not a big thing in terms of energy loss. If it were to lose too much energy, of course, then you would say that, then how do I measure? Because then I get a spread of energy. But in this case, if you compute, this energy loss is very, very tiny, and so it doesn't affect the energy of the electron at all. Okay, so in principle, if you measured the cyclotron frequency, and Arthur Shallow has said that never measure. Arthur Shallow, by the way, was a Nobel laureate for his work on the area of laser physics. He said never measure anything but frequency. Because frequencies can be measured to 1 part in trillion, or 1 part in even 10 to the 15 and so on. Very, very accurate. In fact, in these measurements, cyclotron radiation emission spectroscopy, it is not the frequency measurement that is the limit. It is the systematic errors from the non-constancy of the magnetic field, noise, and so on. Other energy losses if you have a vacuum because of interaction of the electrons with the residual gas and such things. But in any case, this in principle allows a measurement which can go down to tens of milli-electron volts, and even to perhaps electron volts. Milli-electron volts, even lower than this. So their goal is to reach this in about 5 years' time, to measure the beta spectrum from atomic tritium, by the way, not molecular tritium. They can measure things in atomic tritium. Of course, that is better in terms of systematic errors, because molecular tritium decays into final states which are fairly complicated. So there are systematic errors arising from that. In fact, a significant part of that sensitivity limit is due to atomic and molecular effects. Whereas if you use atomic tritium, it's a cleaner system in the final state, and therefore that is one of the reasons why you can reach a sensitivity of 40, or even perhaps with better knowledge even lower, maybe even 10 milli-electron volts. R&D on this is ongoing. There's a beautiful idea which was first propounded in 2009, and they have actually got to do a measurement on single electrons in 2015, and they right now, the bounds on the electron mass are nothing worth reporting, but they will quickly get there as they improve on their R&D. So, for instance, you can see here the kind of electron resolution that they can get for 17.8 keV as a function of frequency. It's rather narrow, as you can see. Okay. The other method is to use internal Bremsstrahlung in electron capture. As I said, the photon can be emitted during electron capture. And then this becomes, instead of a two-body decay, electron capture is a process whereby electron is captured by the nucleus of the atom. It produces a Z-1 nucleus, and it emits a neutrino. Forget about the photon for the time being. So if this is the process, just the electron capture process, you produce a monoenergetic neutrino. On the other hand, if you have a radiative electron capture in which a photon is emitted by the electron is charged, it can emit a photon, then this becomes a three-body process. And obviously, if you measure the photon, it would have a continuous spectrum right up to the end point in this, so the Q value of this process. Unfortunately, it's a process where the branching ratio is very tiny. It's only 10 to the minus 5 or 10 to the minus 6. So the measurement of the IB spectrum from, you have to go to low QEC nuclei, of course, but if you make a precise measurement near the endpoint, in principle, you can measure the mass of the neutrino, the effective mass of the electron type of neutrino. Now, there is another idea of Feynman, which said that you can have resonant enhancement near the endpoint if it so happens that an X-ray transition energy in the final state overlaps with this endpoint energy. This is, as I said, first pointed out by Feynman, and then taken forward by Alvaro de Ruhula in 81. And there seems to be a suitable case in 163 holmium, where the Q value is about 2.8, and there are already 3 experiments mounted using bolometric microcalorimeters operating at millikelvin temperatures. But again, they are still in the phase where they have to improve their setup and so on. So they are still not competitive with the tritium experiment like Katrin, but perhaps they will get there. Also notice that what you will get here is the effective nu E mass. Okay, What you saw in the Katrin experiment, or where you have beta decays, is the effective nu E bar, the anti-neutrino effective mass. Okay? So there is a small, in principle, this could be different if you could get to that accuracy, and if nature shows a difference in mass between particle and antiparticle. Okay, I'll just say a little bit about the searches for heavier neutrino mixings. In fact, in the mid 80s, there was there was a sudden interest because there is a claim of a 17 kV neutrino mixing at rather large mixing, a probability of 3%. We also had something to do with it. We searched for it in another case. This gentleman looked for it in tritium decay, which is a very low end point, and so we thought that there are some problems with this measurement. So we searched for it in a slightly 10 times higher Q value measurement. However, we didn't agree with this scenario, and we could put a bound on that. But of course, we are not the only ones. This idea came to obviously many people. As soon as there is something which is extraordinary is observed, claimed, then many people get to it, and there are about 10 other groups. They didn't support the finding, although a few of them did support this finding. But I think in summary, there's a review article on this, the rise and fall of the 17 kV neutrino in Reviews of Modern Physics in 1995, where the best bounds were about 4 or 5 times better than what we had. And so this bound is of the order of less than 0.17% mixing. So generally it is agreed that there is no evidence for 17 kV neutrino mixing. Okay, now I come to, in the last few minutes, to parity violation in beta decay. This is a different topic, but I think this may be useful for some of the students who are watching it. If parity symmetry is obeyed, which means if you go from x, y, z to minus x minus y, z, then that processes in that mirror universe should also go through equally well. Now, what this means is that if you have a parity odd observable, then, and if parity symmetry is obeyed, then they should be identically zero when you measure it in the lab. In 1957, Li and Yang, in the context of some K-mesonic decays, pointed out that there was no evidence for parity conservation in weak processes. Okay. So immediately people got working, including Professor Wu, who was at Columbia, and she carried out a very difficult but a classic experiment. What she did was to polarize cobalt-60 nucleus, which beta decays, and to preserve this polarization, to polarize it and preserve it, you have to go to very low temperatures of the order of millikelvin. That is what makes the experiment very difficult and challenging. But she managed to do that in the 50s, in the late 50s. And basically, she polarized the nucleus and looked at the asymmetry in the beta decay. So more of beta decay should come out through the south pole or anti-parallel to the spin of the cobalt-60 nucleus as compared to parallel. And at a similar time, Lederman also found angular asymmetry in the basement of the same, university, Columbia University, where she was working. And in basically over a weekend, he found, because they had access to accelerators and therefore pions and therefore muons, that he could confirm that parity was violated in another weak process, namely the decay of stopped muons. So the experiment of Madame Wu is that you polarize cobalt-60 nucleus at, as I said, millikelvin temperatures. You have to use the right salt for doing that. You have to have the cryogenics for doing that. And you have to put a detector in this, and also a small apparatus to magnetize this cobalt salt. So what you see here is the count rate of gamma rays and also of beta particles. So let's concentrate first on the beta particles. So if you look at, so the detector remains at the same place, but you can flip the field. So if you stop cooling the apparatus, then you see a certain asymmetry. You see a certain count rate, and if you were to go to the same cool temperature at 0 time, you would see a higher count rate. But if you allow the apparatus to warm up, then with both directions of the field, you see the same count rate. In other words, there is no asymmetry. With temperature, this polarization disappears. But what is important is that this region, you find an asymmetry. And this would not be there if parity is conserved. As I said, basically what you're looking at is the correlation between the spin polarization of the cobalt and the momentum of the electron. And this is a p odd observable. And so if parity symmetry is obeyed, then if you flip x, y, z to x minus y, z, then the observable becomes minus of that observable. And this can't happen unless this is 0. So if parity symmetry is obeyed, this observable has to be identically 0. The fact that it is not 0 means that parity symmetry is not obeyed. And as it turned out, it was maximally disobeyed. Similarly, the experimental Lederman used a pion beam, and then it stopped this the muons that are produced in the decay of the pions, and then looked at the decay electrons. Now, if the muons are polarized, which it is expected because the pion which decays is a pseudoscalar, it has 0 spin, so you can't, there's no question of polarizing it. But because it decays weakly, and because the muon is accompanied by a neutrino, which is it has its spin aligned with respect to the momentum direction. So the muon also gets polarized. And so if you look at the decay electrons, then they show a finite asymmetry. Now, if you rotate this spin as a function of time, which you can do if you apply external magnetic field. So just as the top precesses in a gravitational field, if you have a muon with a certain spin and you have a magnetic field which is perpendicular, this muon will precess. And so if you have a detector detecting these decay electrons, then you see sometimes a large counting rate and sometimes a small counting rate when the spin is opposite. Okay? So you see a modulation of this count rate, and the way this evolves as a function of time tells you about the magnetic moment of the muon. Or you can use also a fixed time, but you vary the magnetic field, and either way you can get a handle on the magnetic field. So they not only showed that parity symmetry is violated, but they also showed that they could also measure the magnetic moment of the muon. So the reference is also given here. Okay, finally, I'll talk about the helicity of neutrino, of the electron type of neutrino. Now, the helicity for the purpose of this talk is defined as an expectation value of sigma, so which is the spin operator of the neutrino, dotted with the momentum of the neutrino, divided by each of these moduli. Okay? So if this has a preferred spin direction with respect to its momentum, then this would be not equal to 0. But if there is no preferred direction, so if parity symmetry is obeyed, then of course this would be identically 0. So this was done by Goldhaber, Rodzins, and Sanyar and reported in 1958. They measured the helicity of the neutrinos, electron type of neutrinos, indirectly by measuring the polarization of the final states that emit gamma rays. So the polarization, if any, of the neutrinos was transferred to a measurement of the polarization of the photons that de-excite the states that are populated as a result of electron capture. In the case of Europium-152, it gets captured to goes to the 1- state in samarium, and fortunately, nature has given this case. This is the only case, as I said right in the beginning, where the monoenergetic neutrino, its energy is roughly the same as the gamma ray energy. So the recoils that result from neutrino emission can be compensated for by the recoil of the photon when the photon gets emitted. Okay? This is necessary if you want to have a resonant scattering. Now, so the Q value for this is of the order of 1874. When this, of course, this is Q value relates to the ground state transition. When it goes to the excited state, it is 1873 minus 963. And so you can see that these two energies, 911, 963, are roughly of the same order. And so the polarization of the gamma ray that comes following this 1- decay can be measured by a result of small effect in the Compton scattering of magnetized materials. So because of this small difference between scattering from a electron which is polarized parallel to the photon polarization or the reverse, This is a very small effect. It's a fraction of a percent effect. And this is what they measured. And so the measurement of the circular polarization of the resonantly scattered photons, you can look up this paper, led to a measurement of the helicity of the neutrino. So the difference in counter rates with the magnetization one way and magnetization the other way, this is what was measured. And this amounted to only 1.7%, but it was with an error of 0.3%. So the circular polarization of the gamma ray was inferred to be minus 66 plus minus 15%. And then the helicity of the neutrino was inferred to be minus 1 plus minus 0.2. So 20% error on. So this actually qualifies for a 5 sigma measurement of the helicity of the neutrino. So this is one of the classic experiments of helicity of the neutrino. There is another such measurement done in the case of beta decay. It was a slightly indirect measurement done by, again, a person of Indian origin, Palathingal, and he measured it in the case of beta decay. So he measured the effect of neutrinos by measuring the beta decay polarization, and that also came out to be +1 in the case, again, with some error bar. But that was, I think, in the probably mid 60s or 70s. Of course, there are other measurements much later that show that the helicity of the neutrino is -1 with even a better error bar from particles domain. So in any case, these are two examples of parity violation in weak interactions. And unfortunately, Wu did not get the Nobel Prize because there were not only Lederman, there was also a gentleman in Chicago who measured it. And so there are more than even 3 people who measured this. So probably the Nobel Committee decided not to give a Nobel Prize for this. In any case, if they had to share it with Li and Yang, then there was only 1 vacancy. And obviously, there are 3 people who have measured, not listed here, but there is a measurement from Chicago as well. Okay. Now, finally, I come to the last slide. These are some of the open problems. So, as I said, is there CP violation in the neutrino sector? And if there is, then this would throw light on the matter-antimatter asymmetry in universe. This is one of the, as I said, 10 most important problems in, I think, science, not just physics. And probably we might have the hints of an answer already from the T2K experiment. Or are neutrinos their own antiparticles? We don't have an answer to that. And perhaps if the hierarchy is normal, then we would have to wait quite a while for this to happen. Are there more families of neutrinos? There are some smoking gun signals of sterile neutrinos of the order of electron volt by c squared mass, but they have to be borne out by, again, experiments that are ongoing at Fermi Lab and other places. What is the absolute mass of neutrinos? Okay, there are many experiments, some of which we have discussed here. Katrin, if it shows up a positive result, this would be great. If not, then there is another experiment which is already hoping to do that to a level of 40 milli-electron volts, but they would go farther than that because the capability of the experiment is not really exhausted at 40 milli-electron volts. Of course, we have to answer why is this neutrino mass so small. So, of course, when there is a measurement, there are probably hundreds of theories, but probably there are some which are preferred. And so there will be consequences of that theory, which we would again have to look for and then try to go beyond the standard model. Of course, the final open problem that I would like to list here, there are many more, of course, but a very important problem is the detection of Big Bang neutrinos. So these are very low energy neutrinos of the order of hundreds of 100 to 200 micro electron volts, so it makes them very difficult to detect. They should be almost as numerous as the cosmic microwave background radiation. This was measured way back in the 60s, the background radiation from the Big Bang. So as the cosmos expanded, the photons increased their wavelength, and these were, of course, measured, and now they are measured extremely accurately. The so-called cosmic microwave background radiation is, in fact, great tool to understand cosmology, but we are nowhere near that in terms of detecting the equally numerous Big Bang neutrinos. So I think I would like to end this talk here, and thank you all for listening.
Thank you, Professor Datar, for your nice talk and also staying quite much on the time. And in fact, there is time for 2 questions. So I request the participants, if you have a question, please raise your hand. I will see this and unmute your mic so that you can ask the question to the speaker. Okay. The question comes from Deepak Chakravarti.
Yes. Yes, please go ahead, Deepak.
Just a minute. I think I'm having trouble.
You're muted his mic.
Yeah, but I'm unmuting. It's not working. Just give me a second.
Yeah.
We have trouble. Deepak, can you unmute yourself? No. Yeah. Yes. Yeah, please go ahead. Deepak, please go ahead.
Yes, Deepak.
Yeah, you are.
You pose the question.
Now you are unmuted.
I am unmuted now.
Yes, please.
I can hear you. I can hear you. Yeah.
Okay. In one of these slides, you showed.
Yeah.
That the mass of the neutrino is related to the double beta decay probability or whatever lifetime, right?
Yes. Okay, I'll come to
now,
that.
There is a nuclear matrix element there.
Yes.
In the equation.
Yes.
And that may make the situation very pathetic. Isn't it true or is it not true?
Yeah. It is true. So let's say the optimistic estimates are that these may be known to a factor of 2 or so. But if you go to a wider spectrum of theories, maybe this factor goes up to factor of 3 or something. So mu squared would be off by a square of that. But on the other hand, effective mu would be, of course, proportional to the inverse of the nuclear matrix element. And so if this is wrong by a factor of 3 or 4, that would be wrong by a factor of 3 or 4. But it may not be of the order of magnitude. So it's known to certainly less than an order of magnitude.
So one depends only on theoretical calculation, or is there any other experimental handle possible?
No. So there are possibilities of actually trying to get some constraints on this nuclear matrix element by looking at things like transfer matrix elements, or by looking at excitation of this in isospin transfer reactions. So PN reactions, NP reactions, and so you can populate states that are the intermediate states in the double beta decay. So you go from, let's say, Z to Z plus 2, and you can, in principle, this is going through intermediate states in the Z plus 1 excitation spectrum. This can go on up to about 100 MeV or so, and various kinds of angular momentum states up to, I think, 10 or so can also be populated. So basically, you have to map out the matrix elements from the ground state of each of these, the initial nucleus and the final nucleus, to these states through NP reaction. Of course, they have their uncertainty, but then you could use probably some rules if you can get a wide excitation energy spectrum and so on, or you could combine many. But these would be in the form of constraining this nuclear matrix element. So yeah, there are possibilities of that, and they might reduce the uncertainty somewhat. Maybe by a factor of 2 even, possibly. Okay. This has already been shown by Schiffer in a paper. He made measurements of these transfer processes, and this reduced the uncertainty.
But the experiments are probably like 2 particle transfer reactions or something like that?
No, not 2 particle. They're 1 particle. So you would be actually, transferring a proton or a neutron. So you would be exploring states in between.
The intermediate nucleus,
which is the virtual state in this second order process.
Okay.
So I want to ask if Alok has a question. Your mic is unmuted. Alok? Okay. So if there are more questions on the Zoom, please raise your hand. By the time I go to YouTube, some of the participants have some questions. There are a few questions which are, of course, not, they're little elementary, but not part of today's lecture. But nevertheless, maybe it will be nice if you can answer them. But before that, I'll come to one question by Jones Panikar. Is there a reason to expect normal hierarchy or inverted, or vice versa? Maybe looking at similarity with quark sector. Right after this, I'll also take questions from YouTube. Please stay on. Yeah, please, sir, go ahead.
Yeah. I don't think there is any, different theorists will have probably different takes on this, but I think nature will decide ultimately. And it could be either way. There's no particular reason why it should be inverted or no particular reason why it should be normal. Experiment will tell.
Okay. Yeah, as I said, there are some few questions. I know they're not supposed to be part of your today's lecture, but nevertheless, it will be nice if you can briefly answer them. One of them actually was saying that what is mixing angle? So,
what is mixing?
Your neutrino oscillations, you were actually asking that why and how neutrino oscillates and so on. So it's little elementary, but maybe you could briefly, if you can mention about neutrino.
No, it's not elementary. I mean, it's
no. In the sense that it is not thickly part of your talk. So, but now it's a question.
I just mentioned that if they mix, this is what happens.
But
if you were to ask why do these three families of neutrino mix, I think that's a very important question. And I think people are still working at it. I mean, there will be hundreds of papers probably addressing this. Why is theta what it is? Theta 1, 2, theta 1, 3, and theta 2, 3. Why weren't they just 0? And this is, there will be probably, not quite, but almost as many theorists as views on this. So this is an important question. And why nature chose these in the first place, we don't really know. I mean, it's like saying, why did nature choose the electronic charge to be what it is? We don't know the answer at any fundamental level right now. We don't know why the mass of the electron is what it is. So it's on a similar platform that we don't know really why they mix. And also hopefully, when we get measurements and we make measurements of predictions of some of the theories that address these questions, then we might be able to sift and we might be able to throw out some theories from the other, and then we might arrive at some understanding. But right now, we don't have any understanding at all as to why these parameters are what they are. Right now, the idea is to just make measurements of this, because theorists have not advanced to the point where they can make any prediction at all on this.
Yeah,
they can make predictions, but there are such a diversity of predictions that you can't sift. So it's only experiment that will decide. Yeah.
There are also specific questions like saying, what is mixing angle?
What is mixing angle? Oh, this is like, if I were to give you an analogy, suppose I have a frame of reference. Let's take a two-dimensional case. Then I can represent it in one set of axes. But if I rotate that set of axes, I get by an angle theta. Then in that rotated frame, I can represent the same vector, by using this angle. Now, if it is a three-dimensional problem, then you have not one angle, but you have three angles, either angles. So in the same manner, when the neutrinos are produced, they seem to be produced as leptonic eigenstates. But when they propagate as mass eigenstates. So things which have a higher mass will propagate a little more slowly, and things which have a little lesser mass will propagate faster. So in the wave picture, the phase will change depending on what mass it is, and so you will get a different mixture as it propagates. So to start with, if you have an electron type of neutrino, it can be observed as a mu type of neutrino, because when you produce or when you detect, it has to be the leptonic eigenstate. Okay.
Actually, so, Vivek.
Yeah.
I had this confusion forever. When it propagates, why it cannot propagate as a leptonic state?
why it has to go to the other eigenstates and again come back to the electronic state?
No, because
Why it should be like that?
No. When it propagates, it is described by its energy momentum, right?
Yeah,
And because they mix, because you have, you see, if something can mix, it will mix, right? Now what happens is that these three mass eigenstates will propagate differently. That's I mean, a given, because you have to obey the laws of physics. No? So something which which is produced in a momentum eigenstate, if it is a mixture of various masses, it will have different phases, right? And so this is a automatic corollary. But when you observe it, you don't observe. Maybe there are ways in which you can observe the mass as well. If you could somehow devise an experiment in which you could measure the mass irrespective of its flavor, then maybe you could get M1 with some probability, M2 with some probability, M3 with some probability. What you observe, of course, in beta decay is a given set of mixtures, UEI squared times M squared. But this is how they propagate. I mean,
no,
and secondly, yeah, sorry.
In the Katrin experiment, when you wrote the final expression, there is a sum of our mass eigenstates square.
Yes.
But beta decay, there is electronic weak interaction process. Why they should invite again those masses? Why not its own electronic mass? I mean, this question could be very trivial because
that's what I'm saying. No, that's what I'm saying. No, because when you expand a new E, which is what is emitted in beta decay, right? It has a M1 component with a certain probability, M2 component with a certain probability, M3 component with a certain probability. So in principle, if you had enough resolution, okay, this beta decay spectrum should have these three components. So if you make a Fermi-Curie plot, you should have these three components of the Fermi-Curie plot.
I understand, but why?
Yeah. Can I intervene for a second?
Okay.
So, okay, of course, between experts, this discussion is happening, but also there is probably a somewhat simple but maybe uninitiated question. So,
yeah, maybe Deepak, I could talk to you maybe after this.
It is good. No. But we can go back. But I would like this question to be answered.
Okay.
Somebody who is not so much into neutrino physics. So Rajesh, his name, he asked, who discovered neutrino and how he explained to others that there exists the existence of material as neutrino, and how it is proved that they do not contain any charge. So I thought it is good to kind of answer them in some simple words before you go on more rigorous discussion with Deepak.
Sure. Okay. So let's take the first question. How is it? How was the neutrino discovered? Is that is the first question, right?
Yeah.
So it was postulated by Pauli in 1930 because we had to understand the beta decay where the energy spectrum of the betas was continuous. The initial and final nuclei had very definite energies, but the beta seemed to have a variety of energies, right from 0 to the maximum energy possible. So either you had to violate energy conservation. In fact, you have to not only violate energy conservation, but you have to also violate angular momentum and spin statistics. So even statistics would have to be violated. Nevertheless, the conservative view of Pauli was, by the way, there were heavyweights with either point of view. Bohr had this radical viewpoint that maybe energy conservation is not valid in beta decay. Maybe it's followed only on the average and not event by event. Pauli was more conservative. He said, no, we cannot throw energy conservation to the wind, and we have to conserve that. But if you have to conserve that, then there has to be a third particle which has to take away energy, and also it has to have the right angular momentum to conserve angular momentum. So, I mean, energy conservation is as important as momentum conservation, as important as angular momentum conservation. So the proposal of a spin half neutrino solved all of that. Now, it took many years for it to be actually found experimentally, and this was done in a reactor anti-neutrino experiment by Reines and Cohen. So I think I don't have time to explain how it was detected, but I think you can go to the earlier talks which are there
Yes.
on the website, and you will find how it was detected. Okay. Then what was the final question? How do we know that its charge is okay? Now, by the same token, just as we respect the conservation of energy, momentum, angular momentum, we also think that charge is conserved. For instance, if you look at, let's say, a neutron going to a proton, a beta particle, and a neutrino, then neutron is known to have zero charge. In fact, there is a limit bound on the charge of the electric charge of the neutron. Similarly, the charge of the proton is equal to the charge of the electron because hydrogen atoms have zero charge, or at least to an extremely small, tiny limit, they have zero charge. So if charge is conserved, then of course the neutrino has to have zero charge. But what if it is electric charge is not conserved? And this question has also been looked at by that great gentleman Goldhaber, who did that neutrino helicity experiment. And it has been subsequently looked at that by many other people. We had also a very small role to play. We also looked for electric charge non-conserving processes in beta decay, and we also put a bound on such processes. So as far as we know, electric charge is conserved in beta decay. And if that is so, then neutrino has to have zero charge. Okay. Does that answer your question?
No, he's
on YouTube.
Okay, so but I'm sure he must be listening too. Okay. We have one question from Lakshmi. Lakshmi?
Hello, can you hear me?
Yeah, can you speak louder?
Can you speak a little louder, please?
Am I audible? Hello?
Yeah. Yes, please go ahead.
Yeah, just about audible, yes.
Okay, so sir, actually I found one paper that of Katrin. It says that Katrin experiment can be used to measure the cosmic neutrino background. So I mean, how will we do it using that experiment?
Yeah. There is a possibility, but I don't know if it is. Okay, I haven't really looked at that. Yeah, I know. Well, what they are saying is that in tritium beta decay, it decays to a helium-3 nucleus, beta particle, negatively charged electron, and a anti-neutrino, right? Now, what if you take the anti-neutrino from the right side to the left side? Then you can have a neutrino interacting with tritium to produce a helium-3 nucleus and a beta particle, right? Okay. Now you should observe a monoenergetic beta particle. And these guys are sitting right at 18.6 keV. So if they find a peak in that, this could be attributed to the background antineutrinos. I am not up to date as to whether the cross section for such a process would be enough for them to be sensitive. But in any case, they could put a bound on that cross section, because the flux of these neutrinos. This is rather robust, because we know the neutron number to photon number in the universe, and so this could be used to, in principle, detect these. If that I'm not very much aware, if that cross section is such that you can indeed perform such a measurement. But the idea is to look for a monoenergetic beta particle at that endpoint. The region where they are very, very sensitive to, they are looking at anyway, so to speak, with a microscope.
Okay, sir. I don't see any more questions either in Zoom or in the YouTube. So once again, on behalf of all the participants, would like to thank you for taking time and also to come back and finish the part that left, and at the same time also brought about, actually kind of closing your talk with many open problems, I think, that are available for many young scientists on this call, and hopefully we'll have many exciting results coming up in the next 5-10 years. So with that, I would like to close this today's session, but not before once again reminding you the next talk in this series is going to be not on 27th but on 28th. So it's not on Wednesday, but it's on Thursday at same time, 6 o'clock. And that is by Srirup Chaudhary from TIFR, talking on From Nano to Atto, the amazing world of elementary particles. So please come back and join. And as I mentioned, that this is more of a public lecture standard talk. So that means it is more accessible to younger people. So please also pass on this message to other children, other students, and hope to see you back on Thursday. Until then, take care and stay safe. Bye, sir.
Yeah, okay. So let me see. I have to leave. Yeah, I'll talk to Deepak about this a little more on phone. Yeah.
I found it is a little bit too technical.
Yeah.
Okay. Okay.
And maybe